Hi everybody, I hope this video finds you well. Today we're going to be starting on to section 2.6 of your textbook, which talks about the idea of the inverse of a matrix. This video is going to introduce the idea and define what an inverse of a matrix is and investigate what types of matrices actually have inverses. Then in the next video, we'll actually see a process for sort of determining the inverse of a matrix and also learn some properties of the inverse. But let's first start with sort of the discussion or what we're even going to be sort of looking at here. So for all of this video, we're going to always be working with square matrices. So let's say let A be n by n. Okay. What we want to investigate is there a matrix B such that if we do AB, then that's the same as BA, and both of those are actually equal to the identity matrix. So what this is basically asking is if you have a square matrix A, is there a matrix B that acts as the multiplicative inverse? In other words, no matter which side you multiply it on, which we know is a big deal with matrix multiplication, because matrix multiplication normally is not commutative, but we're saying in this case, it doesn't matter if you put B on the right-hand side or on the left-hand side, you'll return the identity matrix. So in other words, i.e., is there a multiplicative inverse? Like if you had numbers, we were thinking like sort of 5 times 1/5 is the same as 1/5 times 5 is equal to 1, right? So 1/5, right, is the multiplicative inverse for normal multiplication of the number 5. Doesn't matter what side we multiply 1/5 on, we're always going to get back to that identity element 1. So we're asking that question for matrices in general. So this is an interesting question, but before we talk about how we can sort of answer this question, we might ask ourselves this: why do we care? I mean, why do we care about investigating this sort of concept of the inverse? Now, of course, we could argue that we care because it's part of the curriculum and it's part of the textbook, and so we care because we got to. But we maybe need a slightly better explanation than that, right? So I want to sort of say two sort of things, right? One, right, is we want to know right? Are matrix operations similar to normal operations? So if you think about it, we've been investigating this idea of whether or not matrix operations, if they're similar to normal operations, for quite a while now. We've seen that matrix addition basically identical to normal addition. Matrix addition is commutative and associative, just like normal addition. Matrix addition has a zero matrix that acts just like the number 0. So matrix addition, and also, of course, matrix subtraction, identical to normal addition and subtraction. Matrix multiplication was a bit different, right? We saw that matrix multiplication was associative, just like normal multiplication, but it was not commutative like normal multiplication. So it's sort of a natural question to ask. Well, we know that in normal multiplication, there's things like the multiplicative inverse out there, but we should go ahead and actually see if that holds up for matrix operations. So it's sort of a natural sort of question to ask, because our investigation thus far has been how similar is matrix algebra to sort of normal arithmetic and algebra. The second reason why we care is going back to sort of solving systems of equations. So let's, suppose we had a system AX equals B. And let's suppose this matrix described above exists. And let's call it A with a little -1 above it, right? So that means A with the little -1 is the same as A with the little -1A equals the identity matrix. Okay, notice that if this thing exists, right? I mean, we don't know that it does yet, but if it does, right, and it has these properties that the multiplicative inverse would have, notice that it would become very easy to solve the system, right? If we have the system ax equals b, we could multiply both sides by this a with the little -1 and do a with the little -1, ax equals a with the little -1, b, right? Then we could recognize that this right here, according to this, is the identity. So this would tell us that I n x equals a inverse b, or a with the little -1. And then, of course, we know that anything times the identity matrix, that's why the identity matrix is the same as the multiplicative identity, is just itself. So this would tell us that x is actually a inverse b, or a -1b. So that would tell us that if this thing exists, we don't know that it does, but if it does exist, we could use it to solve these types of systems. So not only is this sort of a natural question from the perspective of how far can we go with matrix algebra, it also relates back to solving systems of equations. All right, so that hopefully justifies why we care about the inverse here. So let's go ahead and start giving some information about the properties of this inverse, the definition, etc. The first thing we're going to do is we're going to confirm that the inverse, if it exists, is unique. So this is going to be a theorem here. It's called the uniqueness of the inverse. So let's go ahead and set this up and then we'll prove it. So we're going to let A be n by n. Okay. And then we're going to suppose there exists matrices B and C such that AB equals BA equals the identity, and AC equals CA equals the identity. Okay. Then what we're going to do is then B equals C. So what this basically says that is that if you have a matrix A and there are two matrices, right, that both act as the inverse of the matrix, right? This shows you that B acts as the inverse. This shows you that C acts as the inverse. Then those two matrices are the same. In other words, what this basically says is that the inverse matrix, if it exists, is unique. So the general idea of this is that if the inverse exists, then it is unique. So if you have an inverse, there's only one inverse out there. Now, this does not do anything for proving that the inverse exists, because we're just supposing that in this theorem. It's going to be a little while before we actually get to the conditions that confirm that the inverse actually exists. Right now, we're just saying that if it exists, then there is only one of them. So let's go ahead and prove this. So there's lots of different ways to prove this. What we're going to do is we're just going to sort of try to start from one of these assumptions here and work our way as a direct proof to that B equals C. So just keep in mind what we need to show. Our need to show here is that B equals C. So let's go ahead and we can say by sort of assumption, well, we know that AB equals IN. Actually, there's lots of places we could have started. We could have started with AB equals IN, AC equals IN, BA equals IN, CA equals IN. There's tons of different options, but we're going to just start with this guy here. Then what we're going to do is we're going to multiply on both sides by C. But we're going to be careful here. We're going to multiply both sides on the left-hand side by C. So we're going to get CAB equals CIN. Okay. Now let's think a little bit about what we sort of know with this, right? What do we know about this CA here? Well, by assumption, right, we know that CA equals IN. So let's go ahead and replace that and say that that's INB equals CIN. And this step here is since we assumed CA equals IN. Okay, now what can we say about this? Well, by the properties of the identity matrix, right, INB, that's going to be just B, because anything times the identity matrix, regardless of which side, is itself. And CIN is going to be C, because, and again, anything times the identity matrix is itself. So this is by property of IN. And that's exactly what we wanted to show. We just showed that B equals C. So there's our QED and our check mark, right? So what we basically show there is that if you have an inverse, then that inverse must be unique. So if you have an inverse, there is only one inverse out there. All right, so the next thing we're going to do is just introduce a little bit of notation and some terminology about this. And it's sort of nice to do this now because we know we can say the inverse at this point rather than just some inverse, because we know that if there is an inverse, it must be unique. All right, so let's go ahead and give a little bit of notation here. So let's let A be n by n. Then, if there exists an n by n matrix, which we will note A with that little -1, such that A with that A -1 is A with that little -1, A equals in, then we call A with that little -1 the inverse of A. Okay? So this is basically saying that if we can find a matrix such that if you right multiply by that matrix or you left multiply by that matrix, you get the identity matrix, then we notate that with that little -1 above the A, and we call it the inverse of A. We would also say, A is invertible, or older books would say non-singular, if A inverse exists. Okay. We say A is non-invertible, or older books would say singular, if A inverse does not exist. And we will see that it is possible that some matrices are invertible. In other words, they have an inverse, and other matrices out there are non-invertible, and that means their inverse does not exist. And keep in mind, all of this only applies to square matrices, right? There's some extensions of inverses to like non-square matrices, but it's not really something we're covering. So all of this discussion is just about square matrices here. Also, as a note, just keep in mind, note, A with that little -1 is notation, right? It does not mean this, right? There's no such thing as like fractions of matrices. That doesn't make any sense with what we're talking about. So this has no meaning here. We just use that little -1 as notation and convenience because we're used to seeing -1 as something that relates to inverses. So we're just using that as notation here. Okay, so now we have this terminology. We use this notation of A with the little -1 to represent the inverse. A matrix is invertible if it has an inverse. It's non-invertible if it doesn't have an inverse. All right, probably should look at something a little bit more computational. So let's just actually go ahead and do an example of verifying that something is a matrice's inverse. So we've got this little tiny 2x2 matrix here. Matrix A is 2, 3, 2, 2, and we're going to verify that the inverse is -1, 3/2, 1, -1. So how do we confirm that? Well, to verify, we need to show two things. We need to show that A inverse is equal to the identity matrix, and we need to show A inverse A is equal to the identity matrix. In other words, we have to show that it doesn't matter which direction we put that A inverse on, we get the identity matrix. So let's go ahead and do that. So for A inverse, right, if that is supposedly what it is, right, let's go ahead and see 2, 3, 2, 2, and then -1, 3/2, 1, -1. So let's go ahead and use our matrix multiplication. That's going to be row times that column. So if we do that, it looks like we should get -2 and 3, which gives us a 1. Then we're going to take this row times this column, and that looks like we're going to get 3 and -3, so that's going to be 0. Then we're going to take this row and this column, so that's going to be -2 and 2, which is going to be 0. And then finally this row and this column, which is going to give us 3 and -2, which is 1. And we're good there. So that shows us that if we do A and this A with the little -1, we do get the identity matrix. Now, to finish confirming, we have to show that the opposite way, we can't just assume that the opposite way will work because we know matrix multiplication is non-commutative, so we need to confirm it directly. So let's go ahead and do that. So -1, 3/2, 1, -1, and then 2, 3, 2, 2. So just the sort of reverse. So we take this row times this column. If we do that, looks like we should get -2 and 3, which is going to be 1. Then this row times this column, looks like we should get -3 and 3, which is going to be 0. Then this row and this column, so that's going to be 2 and -2, which is going to give us 0. And then finally this row and this column, which is going to give us 3 and -2, which is going to be 1. And that is the identity matrix, so we're all good. So A with this little 1 is the inverse of A. Okay, so that's just directly showing that something is the inverse of another matrix. Now, it's lucky that in this question we were just trying to verify this because we haven't discussed how you would find the inverse. All we're doing here is that since we know A and somebody was kind enough to tell us what the potential inverse is, we're just directly checking that. In the next video, we'll actually learn, given sort of an arbitrary matrix, how to determine this A inverse. But we're not quite there yet. Let's look at one other sort of example, a little bit more abstract here, dealing with sort of verifying something is an inverse. So, for this example, we're going to bring in some terminology that was introduced in some of the suggested exercises, right? So, we're going to have A here be some abstract matrix that is nilpotent of degree 2. And if you've done the suggested exercises, you know that nilpotency basically just means that if a matrix is multiplied with itself a number of times, you result in the zero matrix. So since it's nilpotent of degree 2, that means that when you multiply A with itself, or you do A squared, you get 0. So what we're going to show is we're going to show that the matrix A plus the identity matrix has inverse the identity matrix minus A. So let's go ahead and see if we can prove that. So we need to show two things. What are those two things? Well, we need to show that A plus IN and then IN minus A equals IN. And then we need to show the reverse of that. So IN minus A and A plus IN is also equal to IN. So we need to show both those things. So let's do our little proof here. Well, let's do A plus IN and multiply that with IN minus A. Okay, so we can do some distributing, but we do need to be careful about the order. So if we do that, we take this A and distribute it onto both pieces, but of course it would go in the front. So we would get AIN minus AA, and then distribute this IN into the front of both of those. So plus IN minus INA. All right, let's see if we can clean this up a little bit. Well, first of all, we know that anything that's multiplied by the identity matrix remains the same. So if we do that, we can say that this is the same as A minus that AA plus the identity matrix minus A. Right, that's just using properties of the identity matrix, right, to say that that guy's A, because it doesn't matter which side you multiply the identity matrix on, and since this is a pair of identity matrices, it's also the identity. All right, let's just clean this up a little bit more. We have A and minus A, so we can just get rid of those, and we get minus AA plus IN. All right, a little bit of notation here, right? This minus AA, that's just A times A, so we can write that as minus A squared plus IN. Okay, well, at this point, we sort of just manipulated everything. Now it's probably good to use our assumption. We have this assumption that A is nilpotent of degree 2, meaning that A squared is 0. So we can say that this is minus 0 as a matrix, of course. So I guess if you want, you can call that 0n plus the identity, which of course is just the identity. And so we've shown what we wanted to show, namely that if you do A plus IN times IN minus A, then it is equal to IN. And again, this will be true for any matrix A as long as it has this condition that it's nilpotent of degree 2. Okay, we've got something else to show, which will be very similar. We need to show that in minus a plus in, is equal to in. Oh, we already wrote out that we need to show that, so let's just do this part here. We'll just immediately go into it. Same multiplication. This guy is going to come in on the front of both of these. So we would get INA plus ININ. And then we'll be distributing this minus A onto the front of these guys. So we'll get minus AA and then minus AIN. Let's do the same sort of cleanup with all the identity matrices, right? This first guy, IN times A, that's of course just A. This pair, IN times IN, we can just write that as IN. This guy here, well, we can get a little bit of ahead of ourselves and just call that minus A squared, since we know that's more convenient. And then this minus AIN there, that's just going to be minus A. Then we can clean up this A and minus A. So that just becomes IN minus A squared. And then by assumption, we know that this A squared, because it's nilpotent of degree 2, that is IN minus 0n, which is IN. And notice that this guy took a few fewer steps than we did up here because we sort of knew some of the things that would be useful, so we did it a little faster here. So this really does confirm that, so A plus IN does have inverse IN minus A. Notice, as sort of a side note here, we also have shown A plus IN is invertible, right? In other words, what we mean by that is we have shown that A plus IN is invertible because we've directly shown that it has an inverse, right? So this is just something to sort of keep in mind. If you know something has an inverse, then you know that there's an inverse out there. But if you show that something has an inverse, then you've also shown that it is invertible, right? So we've also, along the way, not only confirmed that this is the inverse, but we've also confirmed that this thing overall has an inverse, namely this guy right here. All right, so now we're ready to start getting into some of the theory behind what types of matrices actually have inverses. So we're almost to that point here. We've just got one sort of small comment to make here that's going to be useful in the major proof that we're about to do. So let's go ahead and take a look at that. So we're going to just give a quick little theorem about solving systems when A is invertible. So our theorem just says this. So let A be n by n invertible matrix. Then the system AX equals B has the unique solution X equals A inverse B for any B. And I believe technically it would be any B that's an element. That looks ugly. Any B that's an element of Rn. And we know it's on Rn because, of course, we're talking about an n by n matrix. But we could just say for any B with implication there. Okay, so this is basically saying that if you do indeed have an invertible matrix, then the system of equations AX equals B, regardless of what that B is, will always have the unique solution, so only a single solution, X equals A inverse B. So to prove this, right, we've actually got to prove two things. First, we need to prove X equals A inverse B is a solution. Then we will prove that it is unique. So how do we prove that this guy is a solution? Well, we just do that by directly evaluating. So let's go ahead and actually write out what we're doing, right? So to check this, directly plug in. So we have AX, right? And we will do A and replacing X with that A inverse B. So A inverse B. Then we know that matrix multiplication is associative, so we can do these multiplications in whatever order we like. So A inverse B. Then we can notice that A inverse, by definition of what it means to be an inverse, is actually IN B. And then by definition, the identity matrix times anything is equal to what it is multiplied by. So this would be equal to B. So we have shown that if we replace X with A inverse B, then it does indeed yield B. So there we go. So x equals A inverse B is a solution. Now we need to show that it is a unique solution, meaning that this is the only solution out there. So let's let y be any solution to ax equals b. Okay? We need to show that y is equal to A inverse B. Okay, so now we're saying, okay, let there be any solution, and we need to show that it is this one particular solution we're talking about. So, since y is a solution, that means AY equals B. All right, that's what it means to be a solution to this system of equations. But all we need to do now is apply the inverse. So let's do that. A inverse AY is A inverse B. We know we can do that because, again, by assumption, A is invertible. Then this would become INY is A inverse B. And then, of course, the identity matrix times anything is just equal to what it is multiplied by. So that's Y equals A inverse B. And there we go, right? We've now shown that Y must be that A inverse B. So this system has unique solution x equals A inverse B. So in other words, what we've shown is that A inverse B is a solution and any solution must be equal to A inverse B. So in other words, A inverse B is the unique solution to this system. So if you ever have a system that has an invertible matrix of coefficients, you know you will only have one unique solution by this theorem. Now, this theorem is useful for solving systems. Obviously, if you know that something has an inverse, or if you know the inverse, you can immediately just solve via matrix multiplication. But this theorem will also be referenced in the sort of last big proof that we'll be doing in this video, which tells us sort of a condition that ties together rank of a matrix and invertibility. So we will be using this theorem in the next proof that we do. So let's see that sort of big theorem that we're going to be talking about here. So, I'm not joking when we say it's a big theorem, so I'm even just calling this big theorem because it ties together the two concepts we've been studying most recently. This says that let A be an n by n matrix, then A is invertible if and only if the rank of A is equal to n. So, in other words, what this is saying is that a matrix is invertible when it has a full rank, where the rank matches the number of columns and the number of rows and the number of columns. And if you know that something has a full rank, it automatically is invertible. Now, this is an if and only if. So to prove this, we actually need to prove two different things. We need to show that if A is invertible, then the rank is equal to n. And if the rank is equal to n, then it is invertible. So we're going to do the sort of easy direction first and then the harder direction second. So the easy, let's make sure we denote, this is our proof here. Easy direction. The easy direction is we're going to try to show that A is invertible implies rank of A is equal to n. Okay? So let's go ahead and do that. And you know what? I don't really like that I already wrote proof here. So let's say what direction we're doing first. A is invertible implies rank of A equals n, and then write our proof underneath that. So here is our proof for that, right? So A is invertible. That's what we're going to assume. So let's then consider the system AX equals B. By the sort of previous theorem, this will always have unique solution. So by the previous theorem that we just did, right, we know that if something is invertible and you consider the system, it will always have a unique solution. But if you stretch back and think about the previous video, we did a full analysis of how rank corresponds to different solution sets. And we said that things only have unique solutions when the rank matches the number of variables. However, so by last video's theorem, unique solution only happens when rank of A equals n. Well, there we go. We proved it. We just showed that if A is invertible, then rank of A equals n. So we've shown that sort of easy direction. If you have something that is invertible, you automatically know that its rank is equal to its number of rows and its number of columns. All right, now we have a harder direction to sort of work through. So the harder direction. The harder direction needs to show the reverse of this. That if rank of A is equal to n, we then need to show that A is invertible. Okay, so let's think about how we're going to do that. What we need to show is there exists a matrix A inverse such that A times A inverse is equal to the identity matrix and A inverse A is equal to the identity matrix. Because, again, how do you show something is invertible? Well, you show that it has an inverse, right? So to show that it has an inverse, we need to show that we can find this matrix that no matter which side we multiply it on, we will always get the identity matrix. So to do this, we're going to set up a little bit of notation here. So we're going to let E sub k equal this column vector. 0, 0, dot, 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 0. Oh, let me give it a little bit more space to sort of write this guy out. So to set this up, we're going to let a little bit of notation, EK, be this sort of thing. 0, down to 0, and then a 1, and then 0, and down to zeros. Where this 1 here, okay, this occurs in the kth row. Okay, so E sub k is a column vector that is all zeros except for a single 1 in the kth row. And these guys are often called the elementary column vectors because they are basically all just zeros except for a single placeholder in exactly the kth position. Okay. All right, now we're going to need these E sub k's because it's going to make us things sort of easier here. Note, as sort of just a side note here, note we can say that IN is actually the matrix E1, E2 down to En, right? We can actually sort of note ahead of time that the identity matrix has this relation to these elementary column vectors, right? The identity matrix is the matrix made up of the elementary column vectors. All right, so now what we're going to do is now consider the system, or the systems, A xk equals E sub k. So we're going to consider these systems with our matrix A times some unknown variable vector equals each of these elementary column vectors. All right. So what do we know about this? Well, since rank of A is equal to n, remember that's the assumption that we have in this part of the proof is that rank of A is equal to n, we know there is a unique solution to each of these systems. So this is back from the previous video. Since the rank of A is equal to n, we know that there is going to be a solution because the augmented matrix won't have any extra rank. So we know that we won't have a chance that any of these don't have solutions. And because the rank is going to match the number of variables, we know that there's going to be a unique solution to each of these. All right, now I don't think I saved quite enough room for the next part of this, so we're just going to add a quick page here. So let's go ahead and do that. So we've got this sort of setup here. So we've got this system, and we know that this system always has a unique solution. So now what we're going to do is we're going to let A inverse equal the matrix x1, x2 down to xn, where each xk is the unique solution to axk equals ek. So we're building this guy as our sort of potential inverse. Now, just because I'm putting the little -1 there doesn't mean that it is the inverse yet. It's just the thing that we hope will be the inverse. And each of these guys we know is unique and will exist because of the fact that the rank of A is equal to n. All right, so what can we say about this? Well, now check A inverse. So let's see what we can say about A inverse. Well, if we do that, what's going to happen is we're going to take the rows of A and multiply by the columns of A inverse. But the columns are neatly defined as x1, x2, all the way down to xn. So if we do this, we will get the matrix AX1, that'll be the first column, then AX2, all the way down to AXN. So now keep in mind, each of these things is actually a column vector because it's taking the matrix A and multiplying by a column of A inverse. But what do we know about each of these things? Well, by definition, AXK are those elementary column vectors. So this is just E1, E2, down to En. But we said earlier that that's exactly In. So we've just shown that A inverse is equal to the identity. That's great, because that's halfway to showing that it is the inverse. We've now shown that A inverse is, or A net negative 1 is equal to the identity. Now we need to show the opposite direction. Now we need to show that A inverse A is equal to the identity. So this is halfway of that direction because we've shown that if you sort of right multiply by this A negative 1, we will get the identity matrix. Now we need to show that if you left multiply, you get the same thing. So let's start with where we just left off. So start with A inverse is the identity. We know that that is true. So let's multiply both sides of this equation by A, but we're going to do that multiplication on the right-hand side. So A inverse A is INA. Okay, now we can clean this up a little bit here, right? We know that this guy right there, that's just going to be A. So we can call this A inverse A is equal to A. Now you might say to yourself, okay, how am I supposed to know that we should multiply both sides by A? Notice that what I've sort of built here is right here, I have my A inverse A, which is ultimately the thing I need to study. So in some ways, it makes sense to multiply both sides on the right-hand side by A, just to build a part of what we really need to sort of study here. Now what we're going to do is we're going to bring this A to the other side. So we've got A inverse A minus A is equal to 0. Now let's go ahead and sort of factor an A out of this. So we can rewrite this as A times A inverse A minus the identity matrix. Now notice, right, if you sort of look at this, you can see why this is the case. If you were to distribute back in, he would go here and give us that, and this guy would go here, and of course when it multiplies with the identity matrix, it just remains as A. So certainly this is a believable step, even though we're maybe not super comfortable doing lots and lots of examples of, factoring in matrix multiplication, but we're all good there. All right, so now we're going to give sort of a little name, right? What we're going to say is we're going to do the same sort of trick that we've been using about thinking about matrices as a collection of column vectors. So we're going to have A inverse A minus IN. We're going to think about it as the sort of matrix y1, y2, down to yn. So in other words, we're letting these y sub k's represent the columns of that matrix. So notice then that we can sort of write this as, well, we can say that we have A and then this y1, y2, down to yn equals 0. Okay, so we're just making a little sort of replacement of this, right? So I guess I should put a little let. Okay. All right, well, notice, again, how matrix multiplication works. The rows of this guy multiply onto the columns of each. So what we end up with, again, we're going to need an extra page. Did not think about how long this proof really was. Once we have that, right, let's just rewrite what we had. We had A and then those y1, y2, down to yn is equal to the 0 matrix over here. So if we do that, that would give us AY1, AY2, all the way down to AYN is equal to the 0 matrix. So if this is equal to the 0 matrix, then each of these must be equal to the 0 column vector. So AY1, or we don't need to say AY1, so AYK is equal to 0 as a column vector for all k. All right. Well, why do we care about this? Well, this is back to a system. It's back to a system with A being the coefficient matrix. So, since rank of A is n, these systems will have unique solution. But we can say a little bit more, right? We know that they have a unique solution, and in fact, we know what the solution is. This is a homogeneous system, and homogeneous systems always have 0 as a solution. So since we know it has a unique solution, that must mean that unique solution is 0. Thus, y sub k is equal to 0 for all k. So we've just shown that these y sub k's are all 0. But what were those y sub k's? Well, we defined those y sub k's right here as the columns of A inverse A minus I sub n. So what we've just shown is, so A inverse A minus I sub n is equal to this, which is a fancy way of just saying A inverse A minus IN is just the 0 matrix. Okay, we're one step away. We're just going to bring this IN over, and we get that A inverse A is equal to the identity matrix. And there we've done it. This guy deserves a QED and maybe even a little smiley face, because that was quite a bit to do there, right? We've just shown that if you left multiply by the inverse, you also get the identity matrix. So, just as a quick sort of summary of everything that we sort of saw there, if we go all the way back to when we started this, we had this easy sort of direction that said we need to show if it's invertible, it has full rank. That was very easy. By being invertible, we knew that it had unique solutions. Whenever you have unique solutions, that means your rank has to be equal to the number of variables. We were done. The harder direction was to say that if the rank is equal to n, then it's invertible. To do that, we attempted to construct A inverse directly. What we did is we took A inverse to be the solutions to A times something equals those elementary column vectors. We knew that each of these would have a unique solution, so we were free in choosing that unique solution as x sub k. Thus, we made this A inverse as that collection of those unique column solutions. Then we checked directly that if we did A times A inverse, that would result, because we had constructed it that way, in those elementary column vectors, which was then the identity matrix. So that showed us that A inverse was indeed the identity matrix. That got us to our halfway point. Then we needed to show that the opposite direction of the multiplication held as well. We did some funny manipulations, basically just building ourselves A inverse by sort of right multiplying by A here. Then we sort of gathered everything to one side and got this system equal to 0. We then sort of studied this component, this A inverse A minus IN, with the sort of goal of trying to show that that was equal to 0, because if we could show that this was equal to 0, then we could show that A inverse A was the same as I sub n. So we sort of defined these special little y's that were the columns of this matrix. Then we looked at sort of the matrix multiplication that resulted in the 0 matrix here. We saw that that matrix multiplication right here was actually equivalent to a set of systems of homogeneous equations. Since the rank was n, which again we had it from the base assumption, those homogeneous systems had a unique solution, and when homogeneous systems have unique solutions, that means the solution is always 0. So we knew that this A inverse A minus I sub n had all columns of zeros, which is the same as saying it's the 0 matrix, which is the same as saying that this matrix had to be identical to this, so that when we subtracted them, we got 0. And we were all done. And of course, at the end, we smiled a little bit because it was a long proof. All right. That is sort of the major theorem of this section. Namely that if you know that the rank of a matrix is n, and a full rank, meaning that the rank matches the rows and columns, then you automatically know that it is invertible, and vice versa. One quick sort of follow-up to this, right? Not super important, but just something to keep in mind, right? If AX equals B has unique solution for some B, then A inverse exists. So as just a quick follow-up to this, this is sort of just saying that as long as one system has a unique solution, then automatically A inverse exists. And this basically just uses the previous theorem, right? All this is saying is that if one system for some B has a unique solution, then you automatically know the rank is n, and then you automatically know that if the rank is n, well, then A inverse exists, right? And of course, this is still A is still n by n. All right. Now, out of all of this, we now have a sort of understanding of when a matrix has an inverse, but we still don't yet know how to find the matrix, that inverse. So we'll be doing that in our next video, and we will be basing it off of sort of the first major step of this proof, which was right here when we sort of said, let's let those columns of the inverse be the solutions to this system. So we'll explore that more in our next video.